Thanks for joining me today. I'll be discussing the smart factory and the top technologies that support a new way of doing business and manufacturing. To get started, I'll take a quick look at a couple of the primary definitions of Industry 4.0 and smart manufacturing from the World Economic Forum and the Boston Consulting Group. Then I'll talk about the focus for visual decisions and what areas we'll cover today. So when we look at the World Economic Forum definition of Industry 4.0 technologies, and they were really the group that initially came up with that term, the very small print over here on the left side is their initial definition of the different technologies that fall underneath there and whether they're already in the mainstream, maturing, or emerging. And they put them into these categories of digital and physical transformation, production philosophies, advanced materials, advanced production processes, human-machine interface, analytics and intelligence, and connectivity and computing. And for us at Visual Decisions, we really focus on those last three. And those are the areas you'll see us focus on later. And for the Boston Consulting Group, and their 9 pillars that they came out with back in 2015 for the factory of the future and the technologies that will really underpin that. They looked at advanced robotics and additive manufacturing and augmented reality and so forth. And for us, again, we're going to be focusing on more of the computer systems, computer technologies, software technologies, portions of that, as opposed to the robotics and the additive manufacturing that are more physical systems in nature. And so when we look at what the scope is for today's presentation with our focus on smart factory systems technologies, it's really the software-based systems as opposed to those physical-based systems or advanced materials and so forth. All right, with that, let's get to the top 5. Number 1 is the Industrial Internet of Things. And when I look at what that is, it's a set of systems and platforms that connect most or all types of devices from the shop floor and collect information from those. Some of the connection options to the shop floor include sensors, PLCs, and other devices, and types of systems in this category or that enable some of the use cases within this category include true I-IoT platforms, such as the one from PTC with ThingWorx, OPC servers, SCADA systems, automation platforms, all play something of a role, either very similar to or overlapping with the I-IoT systems. When we look at how prevalent these systems are, the true IoT platforms are still in the fairly early stages in the marketplace, starting to ramp up, towards that mainstream adoption, while other systems with overlapping capabilities have extremely widespread adoption within manufacturing. So what do these systems do for manufacturing? Well, the most common use cases are OEE improvements, asset monitoring and alerting, quality monitoring, visual controls. And then if we get into additional use cases, there's really too many to mention. It can act as a central hub for your manufacturing data. It integrates with other systems for advanced workflows, as we'll discuss later. But really, it's just limited by your imagination because you're connecting to all of the different devices on your shop floor and then acting as a platform for development. You can really do anything that you want with that data and enable any process that you're looking to help out or augment. And so why is this valuable? Well, because of the breadth of use cases that IoT supports, it can help across many different improvement vectors, primarily productivity, quality, agility, et cetera, reducing cost, improving safety, so forth. The next one, excuse me, that I'll look at is big data. And when I look at the definition for big data, it's really a new set of data storage technologies that support different use cases than traditional relational databases. And Here they talk about the 5 V's traditionally for big data, with volume, the amount of information, the velocity, the speed with which that data is fed into the database, variety, the different types of information that could be included within here, the veracity or the accuracy and precision of the information, and the value of that information as well. But I've seen up to 10 V's with variability, venue, vocabulary, vagueness, and validity also included within there. Some of the different types of systems in this category are some of the newer cloud-based relational databases, Hadoop systems, such as the one from Cloudera, NoSQL databases like MongoDB and so forth. And these systems have become very common in a lot of different industries and use cases in terms of the prevalence. Within manufacturing, the data stores listed above are becoming increasingly frequent with the rise of data sources such as I-IoT that are streaming information very quickly. In addition, some of the traditional data historians, such as OSI Pi, could really be considered large data stores when you look at how they're structured, the purposes of those data systems, and the type of information that they're built to bring in. So what do these systems do with for manufacturing? Manufacturing shop floors generate massive amounts of data every single day. And most of this data is never collected. Most of what's collected is discarded at the end of the shift when the PLC drops that information to reset all of its registers. And then most of the data that's actually saved is never used. And so big data systems eliminate the need for certain decisions about whether to persist information. It makes it easier and cheaper to store new data into those systems than in traditional relational databases. And these systems are built to ingest massive amounts of high-speed data. And so it becomes very simple to make the decision to go ahead and save the information just in case you need it later. The data is then available for analysis, and we'll get to how to do that in a minute, but the data retrieval from these systems is the other critical factor, and they must be built not only to ingest the data very rapidly, but also to support the querying and analysis of that information. So why is it valuable? Well, without big data, many of the use cases that are talked about in other sections wouldn't be possible. So having that detailed process information enables things like correlations of manufacturing data to warranty data, or predictive maintenance use cases, or predictive quality. And being able to have that detailed information, that process variable information, so that I can see how the temperatures are fluctuating over time, or pressures or anything else, and then see where failures occur and start to utilize that detailed information to make those predictions is only possible when I have that detailed information in the first place. And so our first 2 use cases are about getting that information from the process through IoT, and then being able to store it with the big data. Which leads us to our third use case, which is analytics. And that could be in the form of artificial intelligence or machine learning. It could be data mining, it could be statistical analysis, or data visualization. And so when we look at those different terms, machine learning or artificial intelligence are systems that use various forms of learning systems or machine intelligence to augment or automate analysis. Very common application of those systems within manufacturing is predictive analytics. Data mining are solutions that perform various types of automated analysis of data sets to find structural structures within the data, anomalies and other elements within those data sets. Statistical analysis for numerical data sets, statistical analysis can be readily applied to learn what are the key factors about the data. And then data visualization, a picture's worth 1,000 words or even more. Good visualizations can help people understand complex data really at a glance. And for someone that founded a company called Visual Decisions, I'm obviously a big fan of data visualizations. Some of the types of systems in this category, well, there's really too many to be anywhere near complete. But general purpose machine learning solutions are definitely within this category. Data mining solutions, business intelligence systems, predictive analytics, predictive maintenance solutions, and so forth, all fall within this category. How prevalent are they? These systems are everywhere. I guarantee you have one of these types of systems in your company at the very least. And what does it do for manufacturing? Well, these systems provide the predictive maintenance, predictive quality that we talked about earlier. They can automate process analysis. Many visual controls are based on some of the data visualizations that are possible within this category and so forth, and much, much more. It's valuable within manufacturing because they lead to better machine uptime with the predictive maintenance solutions, better quality, higher throughput, identifying deviations from standards, and a lot more. Our next category is augmented and virtual reality. And so we've kind of been building up here. The IoT solutions help us get the data in the first place. The big data stores allow us to persist that information. The analytics allow us to analyze it and come up with various learnings from the information. And now the augmented and virtual reality really helps us to display that information to the people out on the shop floor. And so these systems are interactive experience of real world environment where the objects that reside in the real world are enhanced by computer generated perceptual information, sometimes across multiple sensory modalities, including visual, auditory, haptics, somatosensory, and olfactory. And by the way, that's the Wikipedia definition. In manufacturing, this is mainly accomplished just through phones and tablets or glasses such as a Microsoft HoloLens or similar products. Full virtual reality is where the user is completely immersed in the scene with the glasses. And this also has applications within manufacturing, primarily for things like training or remote operations. So how prevalent are these? AR, or augmented reality, is becoming more common very rapidly. Use cases around remote support with AR really exploded during the pandemic. And now vendors for complex equipment are beginning to ship their manuals and so forth in augmented reality format, along with glasses with which to view those. And then training and inspection use cases are also places where adoption is gaining very rapid acceptance. What does it do for manufacturing? AR has the potential to change how information is distributed within manufacturing. Training can change from something that happens in a classroom or with an experienced expert by your side to something that becomes interactive as you perform anything new within the plant. Standard work can be embedded within the glasses so that people can continually be guided on the standards, and exceptions can be detected and immediately addressed and proper behavior reinforced. And then visual controls within the factory can just be revolutionized by the capabilities of AR. So why is it valuable? It reduces the cost of training. There's improved time to productivity for new workers, cross-training potential, improved quality rates, error proofing, and much, much more. So the final of these 5 technologies really integrating across different systems with horizontal and vertical system integration. And the possibilities are huge. And this is a graphic that I put together from my presentation last week, my webinar last week, around some of the different things that you can do when you combine the IoT shop floor data with the information coming from these other traditional business systems. And in this context, horizontal integration refers to bringing all of the always connected machines from the shop floor into a single system where their real-time status can be communicated and they can respond autonomously to dynamic production requirements. This requires high levels of data transparency and automated collaboration between different systems within the environment. And vertical integration refers to connecting all of the different departments within the organization, such as engineering, product management, IT, finance, sales, field service, et cetera. And this again requires very high levels of data transparency and integration between different systems to facilitate those new workflows across groups and systems. In terms of prevalence, it's still a challenge to achieve real transparency and coordination between multiple systems. This is something that the software industry has been working on literally for decades now, in terms of defining different ways that these systems can interact more easily, whether it was the move to object-oriented programming and the promise of encapsulating the data structures and just having a set of basically API for every object that it could communicate more easily with other objects, to REST APIs and everything else. We're still progressing down that path to true transparency and interoperability between different systems. That said, that point-to-point integration remains the most common method of sharing information across different systems. And as I mentioned up front with the IoT platforms, when they're in use, they can act as that hub for sharing information and data and coordinating that flow across different systems as it relates to the shop floor. So some of the example use cases from last week's presentation on Connect Everything, I covered these in detail last week, so I'll just touch on a few items here. For maintenance, connecting the information from the machines to the maintenance management system enables a lot of additional capabilities within manufacturing. One example is to present autonomous maintenance checklists to the operator each morning or whenever the work needs to be done. And this works best when there's a common process, no matter who's working at the machine that day. And by including work instructions for the tasks, it can greatly simplify job rotations and having people step in for absent workers and so forth. That integration can also be combined between the IoT system and the maintenance management system to automate the ticketing system to minimize the time to repair when downtime occurs by sharing the information about the failure immediately with the maintenance department and getting the ticket issued, information about the nature of the failure, and getting the right people assigned and out to the machine as rapidly as possible. When looking at integration with quality management systems, if you're researching a quality issue, really everything becomes quality data. And that includes data about the machine, any failures, downtime issues, production data, testing information, and much more. And when somebody's researching a quality issue, they should be able to look at a single interface to analyze information across all of those different sources. Planning and scheduling. Combining information from the shop floor with the planning and scheduling systems really creates the possibility of closed loop real-time planning systems that are completely adaptive to the changing conditions on the shop floor. And these types of planning systems are not possible without having that complete shop floor wired into that smart factory solution. And then from an engineering point of view, there are a lot of details behind this, but combining a company's smart factory systems with their product lifecycle systems and other engineering systems allows for significantly enhanced design for manufacturing or design for Six Sigma processes. And just one example of the potential interaction is the automation of product FMEA data collection. So just a few closing thoughts here, quick presentation this week. Excuse me. Yes. Technologies that are not in the top 5. Each of these has a different reason for not making it. Blockchain has tremendous value in particular applications, but it hasn't really found use cases on the shop floor that are as compelling as the technologies in the top 5. Cloud computing has huge penetration and massive acceptance and so forth, but it's not really bringing any new capabilities to manufacturing. It's mainly a revolution for the IT group and how much it costs to maintain these different systems and so forth. Cybersecurity is absolutely necessary component of any of these different initiatives, but it doesn't really help produce more product at a better quality rate. Simulation plays an important role, but I don't feel it provides quite as much value as the technologies in the top 5. Digital twins, and this one may get me in trouble, but I really believe that digital twin is more of a marketing label than anything describing an actual real system capability. So that's it for today's webinar. In the coming weeks, I'll be covering a number of great topics on my webinar Wednesdays. Be sure to go to the Visual Decisions website to register for them. I've actually stopped sending out the emails that let people know about the upcoming webinars. So if you're interested in continuing to attend, I'll probably be announcing them on LinkedIn from now on, as well as maintaining my website event page with the upcoming webinars. So at Visual Decisions, we've been in the business of utilizing information from the shop floor to improve operations since about 2002. We help our customers combine the smart factory and the lean factory to drive improvements to cost, throughput, and quality. And that's why today's topic was so important to me personally. So thank you for joining us today. If you have questions or would like to talk about how to apply these technologies within your company, please reach out to me. You can give me a call, send an email, or go to my Calendly link to set up a meeting directly. Thank you very much. Bye-bye.